Hello and welcome. In this presentation, I will introduce a SAS macro that I developed for calibration of survey weights. Before I get to the macro, first, I want to say a few words about where this macro fits in the SAS software package. As you know, SAS has several procedures for survey sampling. The SurveyCalibrate Macro serves as a supplement to these procedures. The macro not only creates calibration weights, it can also create calibrated replication weights that can be used by these survey procedures. You will need SAS stat and SAS ML to run the macro. In this presentation, I will first talk a little bit about the motivation behind the calibration of survey weights and summarize some commonly used calibration methods that are implemented by the macro. Then I will give some details of the macro parameters, along with the macro's capability. Finally, I will use an example to illustrate how to use this macro and give some closing remarks. In survey sampling, after sample is collected according to a complex sample design, sampling weights are created to reflect the design and to ensure the unbiased estimates for response variables in a finite population, and to estimate the variance. However, sometimes the weights are not ideal. Although the primary goal of a survey is to estimate the population characteristics of certain response variables, it is also reasonable to expect the weighted estimates for auxiliary variables, such as some demographic variables, also match some known information, such as marginal totals in census data. For example, suppose a survey is to estimate the utility usage among restaurants in a county. The total numbers of franchised and the independent restaurants are readily available in the county's record. So if you use the sampling weights to sum up the numbers of restaurants in the sample for each category, the total numbers of the restaurants should match the records on file. However, that's normally not the case as shown in this example. To overcome this problem, calibration technique is often used to modify the weights such that the new weights should be as close as possible to the original weights, and the sum over control variables using these new weights will match the known totals. To solve this calibration problem, first, we need to define the word closeness by using a distance function g to measure the difference between the two sets of weights. Then we need to find a solution by minimize the distance function under a set of constraints. In other words, the calibration weights W tilde are the solution that minimize the distance function under given constraints. The most commonly used calibration methods are linear, exponential, truncated linear, and LOGIT. Each method corresponds to a specific distance function. These are the full calibration methods available in the SurveyCalibrate Macro. When the generalized chi-square distance function is used, it's called the linear method, where you can easily solve the multiplier lambda hat to construct the calibration weights. Although a solution to the linear method always exists, in rare cases, this linear weighting method can yield negative calibration weights. The second method is called the exponential method, which uses the Kuvac-Leibler information distance function. It can be solved by an iterative process such as Newton-Raphson optimization. Although exponential method can ensure positive calibration weights, some weights can be relatively large compared to the rest of the weights. Worse, the solution might not even exist. A special case is when there are two categorical auxiliary variables used in the calibration. The exponential calibration method is equivalent to the traditional raking procedure. The third method is called the truncated linear method. It uses a modified generalized chi-square distance function g shown over here. The ratio of the final calibration weights over the original weights is bounded by L and U. When there is a solution, the truncated linear method creates bounded calibration weights. However, if the lower or upper bounds are ill-chosen, for example, if the lower bound is too high or the upper bound is too low, then the solution might not exist. This process also requires more computational resources. If you're not sure about what bounds you should use, you can leave that to the macro to decide it for you. The macro finds optimal bounds by minimizing the upper bound and maximize the lower bound to avoid extreme calibration weights. The fourth method is called the LOGIT method, also known as the Truncated Exponential Method. It also sets the bounds to the ratio of the final calibration weights over the original weights. The LOGIT method creates calibration weights that are bounded, but it can also run into the problem if the lower bound is set to too high or upper bound is set to too low. Again, if you're not sure about what bounds you should use, you can just leave that to the macro to decide. Now let's take a look at the SurveyCalibrate Macro. These are the parameters listed in order of their importance and how frequently you might need to specify them. I will explain them in detail in the next few slides. The macro parameters can be grouped into two categories. The first is the calibration macro parameters, and the second is the replication macro parameters. And some of these macro parameters can be left blank. These are the 5 parameters you must specify when calling the macro. It's obvious that you should have an input dataset, and you need to provide a name for the output dataset so you won't overwrite your original dataset. Of course, you need to have a weight variable that contains the sampling weights which you will calibrate, as well as the control variables and their known totals for calibration. Both the numeric and the categorical variables can be used as control variables in calibration. However, for categorical variables, you need to create indicator variables for each level in your data before calling the macro to ensure the numbers of levels in the data matches the number of control totals. Several optional macro parameters also control the calibration. You can get more details about these parameters in the paper, which will be available for download from my GitHub site. One important parameter is method, which specifies the calibration method you want to use. You can use any of the 4 methods I mentioned earlier. If you do not specify this parameter, the macro uses the linear method first by default. To ensure the correct variance estimation after the calibration, you also need to use the same calibration method to calibrate replicate weights. If you provide your own replicate weights, the macro not only calibrates the full sample weights, but also calibrates the replication weights you provided. If you do not provide your own replicate weights, you need to specify the second group of parameters to control how the replicate weights to be constructed by the macro for future analysis. You specify these replication macro parameters exactly as you would in any of the survey analysis procedures. So I will skip addressing them in detail here. You can look them up in the SAS documentation. Now let's look at an example to illustrate the usage of this macro. This example uses a dataset from a National Health and Nutrition Examination Survey. In this example, the response variable is vital status, and the couple demographic variables are gender and the POV-AR-RND, which identifies if someone lives in the poverty area. The sampling weights are saved in S weight. For the purpose of illustration, suppose that through other data sources, marginal totals in the surveyed population for the demographic variables POV, ARIND, and gender are known, but they are different from the weighted sums in the sample over these demographic variables. Before I use SurveyCalibrate Macro to calibrate the S weight, because both POV, ARIND, and gender are categorical variables, I first create some indicator variables for gender and residency as shown here before I call the macro. Now I'm ready to call the macro SurveyCalibrate. The input dataset is mortality. I name the output dataset to be final. The sampling weight is S weight. The calibration control variables are the indicator variables we just created in the previous slide, and their known totals are specified by the control total parameter. As I mentioned earlier, these are the 5 parameters required for you to run this macro. I can get a set of calibration weights even I do not specify the rest of these parameters on this slide. However, for this example, I want to use the truncated linear method for the calibration, but I only want to specify the upper bound of the truncation as 2.0, and I want the macro to figure out the lower bound. I also want the macro to construct the calibrated replicated weights using the bootstrap method with the strata and the cluster variables in the dataset mortality. When the macro is finished, these messages in the log report the bound used by the truncated linear method. For this example, the macro finds the optimal lower bound to be 0.35, given the specified upper bound of 2.0. And the calibration weights are saved in the variable called cal as weight in the output dataset final. Now, if we sum over the gender and the residency using the calibrated weights, the results match the known marginal totals. This table compares the analysis of variables vital status and age by using the original sampling weights as weight on the left side and the calibration weights, cal as weight, on the right side. The point estimates and the standard errors changed slightly for this example because of the calibration adjustment. Now let me add a few comments about the calibration and about using this macro in practice. First of all, there's no magic rule for choosing which calibration method should be used. The linear method uses less computing resource and always gives the solution. So it is the first choice for the macro to use if you do not specify a calibration method. But linear method can sometimes yield negative calibration weights for some data. In that case, the second choice is the exponential method. The truncated linear and the LOGIT methods modify the linear and the exponential methods by setting lower and upper bounds to avoid the negative or extreme weights. The downside of these truncation methods is that they are computationally intensive, and sometimes no solution can be found after reasonable numbers of iterations. If you let the macro to find the upper or lower bounds, it also requires additional resources. If you have a large data set, you might want to experiment and set your own lower or upper bounds first to reduce the computation time. In summary, the SurveyCalibrate macro provides a convenient and flexible tool to construct the calibration weights in survey sampling. It accommodates the commonly used calibration methods. It also creates calibration-adjusted replicated weights for future analysis. When you are not sure about an optional parameter, leave it blank and let the macro do its work. You can download the macro and the slides of this presentation from my GitHub website. And if you have any comments or questions, please contact me. Thank you.